Let's get started with our linear algebra review. In this video, I want to tell you what are matrices and what are vectors. A matrix is a rectangular array of numbers written between square brackets. So for example, here is a matrix. I'm going to write a left square bracket and then write in a bunch of numbers. And these could be features for a machine learning problem, or it could be data from somewhere else. But for example, the specific values don't matter. And then I'm going to close it with another right bracket on the right. And so that's one matrix. And here's another example of a matrix. I'm just going to write 1, 2, 3, 4, 5, 6. So a matrix is just another way for saying is a 2D or a two-dimensional array. And the other piece of terminology we need is that the dimension of a matrix is going to be written as the number of rows times the number of columns in the matrix. So concretely, this example on the left, this has 1, 2, 3, 4 rows, and it has 2 columns. And so this example on the left, I'm going to say this is a 4 by 2 matrix, okay? Because it's number of rows by number of columns, so 4 rows, 2 columns. This one on the right, this matrix has 2 rows, so that's the first row, that's the second row, and it has 3 columns, right? That's the first column, that's the second column, that's the third column. So this second matrix, we say it is a 2 by 3 matrix, or we say that the dimension of this matrix is 2 by 3, and sometimes you also see this written out as, in the case of the left, you see this written out as R4 by 2. Or concretely, what people will sometimes say is that this matrix is an element of the set R4 by 2. So this thing here, this just means a set of all matrices that are of dimension 4 by 2. And this thing on the right, sometimes this is written out as a matrix that's an R2 by 3. So if you ever see, 2 by 3. So if you ever see something like this, R4 by 2 or R2 by 3, people are just referring to matrices of a specific dimension. Next, let's talk about how to refer to specific elements of the matrix. And by matrix elements, or elements of the matrix, I just mean the entries or the numbers inside the matrix. So in the standard notation, if A is this matrix here, then A subscript ij is going to refer to the I comma j entry, meaning the entry in the matrix is in the ith row and the jth column. So for example, A11 is going to refer to the entry in the first row and the first column. So that's the first row and the first column. And so, A11 is going to be equal to 1402. Another example, A12 is going to refer to the entry in the first row and the second column. And so A12 is going to be equal to 191. Just a couple more quick examples. Let's see. Let's say A32 is going to refer to the entry in the third row and the second column, right? Because that's 3, 2. So that's equal to 1437. And finally, A41 is going to refer to, this one, right? Fourth row, first column is equal to 147. And if, hopefully you won't, but if you were to write, say, what is A43? Well, that refers to the fourth row and the third column, but, this matrix has no third column, so this is undefined. Or you can think of this as an error. So there's no such element as a A43, so shouldn't be referring to A43. So the matrix gives you a way of letting you quickly organize, index, and access lots of data. And in case I seem to be tossing up a lot of concepts, a lot of new notation very rapidly, you don't need to memorize all this, but on the course website, where we have posted the lecture notes, we also have all of these definitions written down. So you can always refer back, either to these slides posted on the course website or to the lecture notes if you forget, like, well, A41 is that, which row, which column is that. Don't worry about memorizing everything now. You can always refer back to the written materials on the course website, use that as a reference. So that's what a matrix is. Next, let's talk about what is a vector. A vector turns out to be a special case of a matrix. A vector is a matrix that has only one column. So if you have an n by 1 matrix, then that's remember, right? N is the number of rows, and 1 here is the number of columns. So a matrix with just one column is what we call a vector. So here's an example of a vector, right? With, I guess I have n equals 4 elements here. So we also call this thing, another term for this is that this is a 4-dimensional vector. It just means that this is a vector with 4 elements, with 4 numbers in it. And just as earlier for matrices, you saw this notation like R3 by 2 to refer to 3 by 2 matrices, right? For this vector, we're going to refer this to this as a vector in the set R4. So this R4, again, just means a set of all 4-dimensional vectors. Next, let's talk about how to refer to elements of the vector. We're going to use the notation yi to refer to the ith element of the vector y. So if y is this vector, y subscript I is the ith element. So y1 is the first element, is equal to 460. Y2 is equal to the second element, right? 232. That's the first, that's the second. Y3 is equal to 315, and so on. And only y1 through y4 are defined because this is a 4-dimensional vector. Also, it turns out that there are actually 2 conventions for how to index into a vector. And here they are. Sometimes people will use 1 index and sometimes 0 index vectors. So this example on the left is a 1 index vector where the elements we write as y1, y2, y3, y4. And this example on the right is an example of a 0 index vector where we start the indexing of the elements from 0. So the elements go from y0 up to y3. And this is a little bit like the arrays of some programming languages, right, where the arrays can either be indexed starting from 1, so the first element of an array is sometimes say y1, this is kind of C++ notation, I guess, and sometimes is 0 index, depending on what programming language you use. So it turns out that in most of math, the 1 index version is more common. But for a lot of machine learning applications, 0 index vectors gives us a more convenient notation. So what you should usually do is, unless otherwise specified, you should assume that we're using 1 index vectors. In fact, throughout the rest of these videos on linear algebra review, I will be using 1 index vectors. But just be aware that when we talk about machine learning applications, sometimes I'll explicitly say when we need to use 0 index vectors as well. Finally, by convention, usually when writing matrices and vectors, most people will use uppercase to refer to matrices. So we use capital letters like A, B, C, X to refer to matrices, and usually we'll use lowercase like A, B, X, Y to refer to either numbers, just real numbers, or scalars, or to vectors. But this isn't always true, but this is the more common notation where we use lowercase y to refer to vector, and we usually use uppercase to refer to a matrix. So you now know what are matrices and vectors. Next, we'll talk about some of the things you can do with them. In this video, we'll talk about matrix addition and subtraction, as well as how to multiply a matrix by a number, also called scalar multiplication. Let's start with an example. Given 2 matrices like these, let's say I want to add them together. How do I do that? And so what does addition of matrices means? It turns out that if you want to add 2 matrices, what you do is you just add up the elements of these matrices one at a time. So my result of adding 2 matrices is going to be itself another matrix. And the first element I get just by taking 1 and 4 and multiplying them and adding them together. So I get 5. The second element I get by taking 2 and 2 and adding them. So I get 4. 3 plus 0 is 3, and so on. I'm going to stop changing colors, I guess. And on the right is 0.5, 10, and 2. And it turns out you can add only 2 matrices that are of the same dimension. So this example is a 3 by 2 matrix because this has 3 rows and 2 columns, so that's 3 by 2. This is also a 3 by 2 matrix, and the result of adding these two matrices is a 3 by 2 matrix again. So you can only add matrices of the same dimension, and the result will be another matrix that's of the same dimension as the ones you just added. Whereas in contrast, if we were to take these two matrices, so this one is a 3 by 2 matrix, so again, 3 rows, 2 columns. This here is a 2 by 2 matrix. And because these two matrices are not of the same dimension, you know, this is an error. So you cannot add these two matrices, and you know, their sum is not well defined. So that's matrix addition. Next, let's talk about multiplying matrices by a scalar number. And a scalar is just maybe an overly fancy term for, you know, a number or a real number. Right? This scalar just means real number. So let's take the number 3 and multiply it by this matrix. If you do that, the result is pretty much what you'd expect. You just take your elements of the matrix and multiply them by 3 one at a time. So, you know, 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. And let's see, I'm going to stop changing colors again. 0 times 3 is 0. 3 times 5 is 15. And 3 times 1 is 3. And so this matrix is the result of multiplying that matrix on the left by 3. And you notice, again, this is a 3 by 2 matrix, and the result is a matrix of the same dimension. This is a 3 by 2. Both of these are 3 by 2 dimensional matrices. And by the way, you can write multiplication, you know, either way. So I had 3 times this matrix. I could also have written this matrix 1, 0, 2, 5, 3, 1, right? I just copied this matrix over to the right. I can also take this matrix and multiply this by 3. So whether it's 3 times the matrix or the matrix times 3 is the same thing, and this thing here in the middle is the result. You can also take a matrix and divide it by a number. So turns out taking this matrix and dividing it by 4, this is actually the same as taking the number 1/4 and multiplying it by this matrix, 4, 0, 6, 3. And so, you know, you can figure the answer. The result of this product is, you know, 1/4 times 4 is 1, 1/4 times 0 is 0, 1/4 times 6 is, 3 halves. That 6 over 4 is 3 halves, and 1/4 times 3 is 3/4. And so that's the result of computing, you know, this matrix divided by 4. That gives you the result. Finally, for a slightly more complicated example, you can also take these operations and combine them together. So in this calculation, I have 3 times a vector plus a vector minus another vector divided by 3. So just make sure we know what these are, right? This multiplication, this is an example of scalar multiplication, because I'm taking 3 and multiplying it. And this is, you know, another scalar multiplication, or I'm going to write scalar division, I guess. This really just means 1/3 times this. And so if we evaluate these two operations first, then what we get is this thing is equal to, let's see, so 3 times that vector is 3, 12, 6, plus my vector in the middle, which is a 0, 0, 5, minus 1, 0, 2/3, right? And again, just to make sure we understand what's going on here, this plus symbol, that is matrix addition, right? Or really, since these are vectors, remember vectors are special cases of matrices, right? This, we can also call this vector addition. And this minus sign here, this is, again, you know, matrix subtraction. But because this is a n by 1, really a 3 by 1 matrix, that this is actually a vector. So this is also vector. Just call this matrix a vector subtraction as well. Okay? And finally, to wrap this up, this therefore gives me a vector whose first element is going to be 3 plus 0 minus 1. So that's 3 minus 1, which is 2. The second element is 12 plus 0 minus 0, which is 12. And the third element of this is, 6 plus 5 minus 2/3, which is 11 minus 2/3, so that's 10 and 1/3. And I'm going to close my square bracket. And so this gives me a 3 by 1 matrix, which is also just called a 3-dimensional vector, right? Which is the outcome of this calculation over here. So that's how you add and subtract matrices and vectors and multiply them by scalars, so by real numbers. So far, I've only talked about how to multiply matrices and vectors by scalars, by real numbers. In the next video, we'll talk about a much more interesting step of taking two matrices and multiplying two matrices together. In this video, I'd like to start talking about how to multiply together two matrices. We'll start with a special case of that, of matrix-vector multiplication, of multiplying a matrix together with a vector. Let's start with an example. Here's a matrix, and here's a vector, and let's say we want to multiply together this matrix with this vector. What's the result? Let me just work through this example, and then we will step back and look at just what the steps were. It turns out the result of this multiplication process is going to be itself a vector. And I'm just going to work through this first, so later we'll come back and see, just what I did here. To get the first element of this vector, I'm going to take these two numbers and multiply them with the first row of the matrix and add up the corresponding numbers. I'm going to take 1 multiplied by 1, and take 3 and multiply by 5, and that's what? That's 1 plus 15, so that gives me 16. I'm going to write 16 here. Then for the second element, I'm going to take the second row and multiply it by this vector. So I have 4 times 1 plus 0 times 5, which is equal to 4. So I get a 4 there. And finally, for the last one, I have 2, 1 times 1, 5. So I have 2 by 1 plus 1 by 5, which is equal to 7. And so I get a 7 over there. Okay? And it turns out that the result of multiplying that's a 3 by 2 matrix by a 2 by 1 matrix, there's also just a 2-dimensional vector. The result of this is going to be a 3 by 1 matrix. So that's why I get a 3 by 1 matrix. In other words, a 3 by 1 matrix is just a 3-dimensional vector. So I realized that I did that pretty quickly, and you're probably not sure if you can repeat this process yourself, but let's look in more detail at what just happened and what this process of multiplying a matrix by a vector looks like. Here are the details of how to multiply a matrix by a vector. Let's say I have a matrix A and I want to multiply that by a vector X. The result is going to be some vector Y. So the matrix A here is an m by n dimensional matrix, so m rows and n columns, and I'm going to multiply that by an n by 1 matrix, or in other words, by an n-dimensional vector. It turns out this n here has to match this n here. In other words, the number of columns in this matrix, so the number of columns, there are going to be n columns. Number of columns here has to match the number of rows here, or it has to match the dimension of this vector. And the result of this product is going to be an m-dimensional vector y. Okay, so in other words, the number of rows here, m, is going to be equal to the number of rows in this matrix A. So how do you actually compute this vector y? Well, it turns out to compute this vector y, the process is to get yi, multiply a's ith row with the elements of the vector x and add them up. So here's what I mean. In order to get the first element of y, that first number, whatever that turns out to be, we're going to take the first row of the matrix A and multiply them one at a time with the elements of this vector x. So we're going to take this first number, multiply by this first number, then take the second number, multiply by this second number, take this third number, whatever that is, multiply the third number, and so on until we get to the end. And then we're going to add up the results of these products. And the result of adding that up is going to give us this first element of y. Then when we want to get the second element of y, like say this element, the way we do that is we take the second row of A and we repeat the whole thing. So we take the second row of A and multiply elements y, so the elements of x, and add up the results of the products, and that would give me the second element of y. And you keep going to get, and then I'm going to take the third row of A, multiply elements y's, with the vector of x, sum up the results, and then I get the third element, and so on until I get down to the last row, like so. Okay, so that's the procedure. Let's do one more example. Here's the example. So let's look at the dimensions, right? Here, this is a 3 by 4-dimensional matrix. This is a 4-dimensional vector, or a 4 by 1 matrix. And so the result of this product is going to be a 3-dimensional vector. So I'm going to write, a vector with room for 3 elements. Let's carry out the products. So for the first element, I'm going to take these 4 numbers and multiply them with the vector x. So I have 1 times 1 plus 2 times 3 plus 1 times 2 plus 5 times 1, which is equal to, that's 1 plus 6 plus 2 plus 6, which gives me 14. And then for the second element, I'm going to take this row now and multiply it with this vector. So I start with 0 times 1 plus 3, right? So 0 times 1 plus 3 times 3 plus 0 times 2 plus 4 times 1, which is equal to, let's see, that's 9 plus 4, which is 13. And finally, for the last element, I'm going to take this last row. So I have minus 1 times 1, minus 2, or really this is plus negative 2, I guess, times 3 plus 0 times 2 plus 0 times 1. And so that's going to be minus 1 minus 6, which is going to be negative 7. And so that's negative 7. Okay, so my final answer is this vector 14, just to write it out without the colors, 14, 13, negative 7. And as promised, the result here is a 3 by 1 matrix. So that's how you multiply a matrix and a vector. I know that a lot just happened on this slide, so if you're not quite sure where all these numbers went, feel free to pause the video and sort of take a slow, careful look at this big calculation that we just did and try to make sure that you understand the steps of what just happened to get us these numbers 14, 13, and 7. Finally, let me show you a neat trick. Let's say we have a set of 4 houses, so 4 houses with 4 sizes like these, and let's say I have a hypothesis for predicting what is the price of a house. And let's say I want to compute, h of x for each of my 4 houses here. It turns out there's a neat way of posing this, applying this hypothesis to all of my houses at the same time. It turns out there's a neat way to pose this as a matrix vector multiplication. So here's how I'm going to do it. I'm going to construct a matrix as follows. My matrix is going to be 1, 1, 1, 1 times, and I'm going to write down the sizes of my 4 houses here. And I'm going to construct a vector as well. And my vector is going to be this vector of 2 elements. That's these minus 40 and 0.25. That's these 2 coefficients, theta 0 and theta 1. And what I'm going to do is take this matrix and that vector and multiply them together. Right? That times is this multiplication symbol. So what do I get? Well, this is a 4 by 2 matrix. This is a 2 by 1 matrix. So the outcome is going to be a 4 by 1 vector. Right? So let me, so this is going to be a 4 by 1 matrix is the outcome, or really a 4-dimensional vector. So let me write in what are my 4 elements. I'm going to have 4 row numbers here. Now it turns out the first element of this result, right, the way I'm going to get that is I'm going to take this and multiply it by this vector. And so this is going to be minus 40 times 1 plus 0.25 times 2104. By the way, on the earlier slides, I was writing 1 times minus 40 and 2104 times 0.25, right? But the order doesn't matter, right? Minus 40 times 1 is the same as 1 times minus 40. And this first element, of course, is h applied to 2104. So it's really the predicted price of my first house. Well, how about the second element? Hope you can see where I'm going. To get the second element, right, I'm going to take this and multiply it by my vector, and so that's going to be minus 40 times 1 plus 0.25 times 1416, and so this is going to be h of 1416, right, and so on for the third and the and so on for the third and the fourth elements of this 4 by 1 vector. And just be clear, right? This thing here that I just drew the green box around, that's a row number, okay? That's a single row number. And this thing here that I drew the magenta box around, the purple magenta color box around, that's a row number, right? And so this thing on the right, this thing on the right overall, this is a 4 by 1 dimensional matrix with a 4-dimensional vector. And the neat thing about this is that when you're actually implementing this in software, so when you have 4 houses and when you want to use your hypothesis to predict the prices, to predict the price y of all of these 4 houses, what this means is that you can write this in one line of code. When we talk about Octave and programming languages later, you can actually write this in one line of code. You write prediction equals my data matrix times parameters, right? Where data matrix is this thing here, and parameters is this thing here, and this times is a matrix vector multiplication. And if you just do this, then this variable, prediction, sorry about my bad handwriting, but if you just implement this one line of code, assuming you have an appropriate library to do a matrix vector multiplication, if you just do this, then prediction becomes this 4 by 1 dimensional vector on the right that just gives you all the predicted prices. And the alternative, to doing this as a matrix vector multiplication would be to write something like, for I equals 1 to 4, right? And you have, say, 1,000 houses, it'd be for I equals 1 to 1,000 or whatever. But then you have to write a prediction, of I equals, and then do a bunch more work over there. And it turns out that when you have a large number of houses, if you were trying to predict the prices of not just 4, but maybe of 1,000 houses, then it turns out that when you implement this in the computer, implementing it like this, in any of various languages, this is not true only for Octave, but for C++, Java, Python, other languages as well. It turns out that by writing code in this style on the left, it allows you to not only simplify the code, because now you're just writing one line of code rather than a for loop with a bunch of things inside, but for subtle reasons that we'll see later, it turns out to be much more computationally efficient to make predictions on all of the prices of all of your houses, doing it the way on the left than the way on the right, than if you were to write your own for loop. And I'll say more about this later when we talk about vectorization. But so by posing prediction this way, you get not only a simpler piece of code, but a more efficient one. So that's it for matrix vector multiplication, and we'll make good use of these sorts of operations as we develop the linear regression and other models further. But in the next video, we're going to take this and generalize this to the case of matrix-matrix multiplication. In this video, we'll talk about matrix-matrix multiplication, or how to multiply two matrices together. When we talk about the method in linear regression for how to solve for the parameters theta 0 and theta 1 all in one shot, so that without needing an iterative algorithm like gradient descent, when we talk about that algorithm, it turns out that matrix-matrix multiplication is one of the key steps that you need to know. So let's, as usual, start with an example. Let's say I have two matrices and I want to multiply them together. let me again just work through this example, and then I'll tell you a little bit what happened. So the first thing I'm going to do is I'm going to pull out the first column of this matrix on the right. And I'm going to take this matrix on the left and multiply it by, a vector that's just this first column. Okay? And it turns out if I do that, I'm going to get the vector 11, 9. So this is the same matrix vector multiplication as you saw in the last video. I worked this out in advance, so I know it's 11, 9. And then the second thing I'm going to do is I'm going to pull out the second column of this matrix on the right, and I'm then going to take this matrix on the left, right? So take that matrix and multiply it by that second column on the right. So again, this is a matrix vector multiplication step, which you saw from the previous video. And it turns out that if you multiply this matrix and this vector, you get 10, 14. And by the way, if you want to practice your matrix vector multiplication, feel free to pause the video and check this product yourself. Then I'm just going to take these two results and put them together, and that'll be my answer. So it turns out the outcome of this product is going to be a 2 by 2 matrix, and the way I'm going to fill in this matrix is just by taking my elements 11, 9 and plugging them here, and taking 10, 14 and plugging them into the second column. Okay, so that was the mechanics of how to multiply a matrix by another matrix. You basically look at the second matrix one column at a time, and then you assemble the answers. And again, we'll step through this much more carefully in a second. But just want to point out also, this first example is a 2 by 3 matrix. I'm multiplying that by a 3 by 2 matrix, and the outcome of this product, it turns out to be a 2 by 2 matrix. And again, we'll see in a second why this was the case. All right, that was the mechanics of the calculation. Let's actually look at the details and look at what exactly happened. Here are the details. I have a matrix A, and I want to multiply that with a matrix B, and the result will be some new matrix C. And it turns out you can only multiply together matrices whose dimensions match. So A is an m by n matrix, so m rows, n columns. And I'm going to multiply that with an n by o matrix. And it turns out this n here must match this n here. So the number of columns in the first matrix must equal to the number of rows in the second matrix. And the result of this product will be a m by o matrix, like the matrix C here. And in the previous video, everything we did corresponded to the special case of O being equal to 1. Okay, that was to the case of B being a vector. But now we're going to deal with the case of values of O larger than 1. So here's how you multiply together the two matrices. In order to get, what I'm going to do is I'm going to take the first column of B and treat that as a vector, and multiply the matrix A with the first column of B. And the result of that will be a m by 1 vector, and I'm going to put that over here. Then I'm going to take the second column of B, right? So this is another n by 1 vector. So this column here, this is right n by 1. It was an n-dimensional vector. Going to multiply this matrix with this n by 1 vector. The result will be a m-dimensional vector, which I'm going to put there, and so on. Okay, and so and then I'm going to take the third column, multiply it by this matrix. I get a m-dimensional vector, and so on until you get to the last column times the matrix times the last column gives you the last column of C. Just to say that again, the ith column of the matrix C is obtained by taking the matrix A and multiplying the matrix A with the ith column of the matrix B for the values of I equals 1 to up through O. Okay, so this is just a summary of what we did up there in order to compute the matrix C. Let's look at just one more example. Let's say I want to multiply together these two matrices. So what I'm going to do is first pull out the first column of my second matrix. That was my matrix B on the previous slide, and I therefore have this matrix times that vector, And so, let's do this calculation quickly. This is going to be equal to, right, 1, 3 times 0, 3, so that gives 1 times 0 plus 3 times 3. And the second element is going to be 2, 5 times 0, 3, so that's going to be 2 times 0 plus 5 times 3. And that is 9, 15. Okay? Oh, actually, let me write that in green. So this is 9, 15. And then next, I'm going to pull out the second column of this and do the corresponding calculation. So that's this matrix times this vector 1, 2. Let's also do this quickly. So that's 1 times 1 plus 3 times 2. So just that was that row. And let's do the other one. So let's see. That gives me what? 2 times 1 plus times 2. And so that is going to be equal to, let's see, 1 times 1 plus 3 times 1 is 4. And 2 times 1 plus 5 times 2 is 12. So now I have these two, and so my outcome, so the product of these two matrices is going to be, this goes here, and this goes here. So I get 9, 15, and 4, 12. And you may notice also that the result of multiplying a 2 by 2 matrix with another 2 by 2 matrix, the resulting dimension is going to be that first 2 times that second 2. So the result is itself also a 2 by 2 matrix. Finally, let me show you one more neat trick that you can do with matrix-matrix multiplication. Let's say as before that we have 4 houses whose prices we want to predict. Only now we have 3 competing hypotheses shown here on the right. So if you want to apply all 3 competing hypotheses to all 4 of your houses, it turns out you can do that very efficiently using a matrix-matrix multiplication. So here on the left is my usual matrix, same as from the last video, where these values are my housing prices, and I've put ones here on the left as well. And what I'm going to do is construct another matrix where here the first column is this minus 40 and 0.25, and the second column is this 200, 0.1, and so on. Okay? And it turns out that if you multiply these two matrices, what you find is that this first column, let me draw that in blue. Well, how do you get this first column, right? Our procedure for matrix-matrix multiplication is, the way you get this first column is you take this matrix and you multiply it by this first column. And we saw in the previous video that this is exactly the predicted housing prices of the first hypothesis, right, of this first hypothesis here. And how about the second column? Well, how do you get the second column? The way you get the second column is, well, you take this matrix and you multiply it by this second column. And so the second column turns out to be the predictions of the second hypothesis up there. And similarly for the third column. And so I didn't step through all the details, but hopefully you feel free to pause the video and check the math yourself and check that what I just claimed really is true. But it turns out that by constructing these two matrices, what you can therefore do is very quickly apply all 3 hypotheses to all 4 house sizes to get all 12 predicted prices output by your 3 hypotheses on your 4 houses. So with just one matrix multiplication step, you manage to make 12 predictions. And even better, it turns out that in order to do that matrix multiplication, there are lots of good linear algebra libraries in order to do this multiplication step for you. And no matter sort of pretty much any reasonable programming language that you might be using, certainly all the top 10 most popular programming languages will have great linear algebra libraries. And there'll be good linear algebra libraries that are highly optimized in order to do that matrix-matrix multiplication very efficiently, including taking advantage of any sort of parallel computation that your computer may be capable of, whether your computer has multiple cores, or sort of multiple processors, or sort of within a processor, sometimes there's parallelism as well, called SIMD parallelism, that your computer can take care of. And you should be able to, and there are very good free libraries that you can use to do this matrix-matrix multiplication very efficiently, so that you can very efficiently make lots of predictions of lots of hypotheses. Matrix multiplication is really useful since you can pack a lot of computation into just one matrix multiplication operation. But you should be careful of how you use them. In this video, I want to tell you about a few properties of matrix multiplication. When working with just real numbers, or when working with scalars, multiplication is commutative. And what I mean by that is if you take 3 times 5, that is equal to 5 times 3. And the ordering of this multiplication doesn't matter. And this is called the commutative property of multiplication of real numbers. It turns out this property that you can reverse the order in which you multiply things, this is not true for matrix multiplication. So concretely, if A and B are matrices, then in general, A times B is not equal to B times A. So just be careful of that. It's not okay to arbitrarily reverse the order in which you multiply matrices. So we say that matrix multiplication is not commutative. It's a fancy way of saying it. As a concrete example, here are two matrices. This matrix 1100 times 0020. And if you multiply these two matrices, you get this result on the right. Now, let's swap around the order of these two matrices. So I'm going to have taken these two matrices and just reverse them. It turns out if you multiply these two matrices, you get this second answer on the right. And, well, clearly, right, these two matrices are not equal to each other. So, in fact, in general, if you have a matrix operation like A times B, if A is an m by n matrix and B is an n by m matrix, just as an example, then it turns out that the matrix A times B, right, is going to be an m by m matrix, whereas the matrix B times A is going to be an n by n matrix. So the dimensions don't even match, right? So if A times B and B times A may not even be the same dimension. In the example on the left, I had all 2 by 2 matrices, so the dimensions were the same, but in general, reversing the order of the matrices can even change the dimension of the outcome. So matrix multiplication is not commutative. Here's the next property I want to talk about. So when talking about real numbers or scalars, let's say I have 3 times 5 times 2. I can either multiply 5 times 2 first, and I can compute this as 3 times 10, or I can multiply 3 times 5 first, and I can compute this as 15 times 2, and both of these give you the same answer, right? Both of these is equal to 30. So if it doesn't matter whether I multiply 5 times 2 first, or whether I multiply 3 times 5 first, because sort of, 3 times 5 times 2 is equal to 3 times 5 times 2. And this is called the associative property of row number multiplication. It turns out that matrix multiplication is associative. So concretely, let's say I have a product of 3 matrices, A times B times C. Then I can compute this either as A times B times C, or I can compute this as A times B times C, and these will actually give me the same answer. I'm not going to prove this, but you can just take my word for it, I guess. So just to be clear what I mean by these two cases, let's look at the first one right? This first case. What I mean by that is if you actually want to compute A times B times C, what you can do is you can first compute B times C, so that D equals B times C, then compute A times D. And so this is really computing A times B times C. Or, for this second case, you can compute this as you can set E equals A times B, then compute E times C, and this is then the same as A times B times C, and it turns out that both of these options will give you, is guaranteed to give you the same answer. And so we say that matrix multiplication does enjoy the associative property. Okay? And don't worry about the terminology associative and commutative. That's what it's called, but I'm not really going to use this terminology later in this class, so don't worry about memorizing those terms. Finally, I want to tell you about the identity matrix, which is a special matrix. So let's again make the analogy to what we know of real numbers. So when dealing with real numbers or with scalar numbers, the number 1 is, you can think of it as the identity of multiplication. And what I mean by that is that for any number z, the number 1 times z is equal to z times 1, and that's just equal to the number z, right? For any real number z. So 1 is the identity operation and sort of satisfies this equation. So it turns out that in the space of matrices, there's an identity matrix as well, and is usually denoted I, or sometimes we write it as I of n by n if we want to make explicit the dimension. So I subscript n by n is the n by n identity matrix. And so there's a different identity matrix for each dimension n. And here are a few examples. Here's the 2 by 2 identity matrix. Here's the 3 by 3 identity matrix. Here's the 4 by 4 identity matrix. So the identity matrix has the property that it has 1s along the diagonals, right, and so on, and 0 everywhere else. And so, by the way, the 1 by 1 identity matrix, is just the number 1. It's the 1 by 1 matrix with just 1 in it. So it's not a very interesting identity matrix. And informally, when I or others are being sloppy, very often we'll write the identity matrix using the following notation. When I draw, square brackets, just write 1, 1, 1, dot, 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 1, and then we'll maybe somewhat sloppily write a bunch of zeros there. And these zeros on this big 0 and this big 0, that's meant to denote that this matrix is 0 everywhere except for the diagonal. So this is just how, I might sloppily write the identity matrix. And it turns out that the identity matrix has this property that for any matrix A times identity equals I times A equals A. So that's a lot like this equation that we had up here, right? So that 1 times z equals z times 1 equals z itself. So I times A equals A times I equals A. Just to make sure we have the dimensions right. So if A is an m by n matrix, then this identity matrix here, that's an n by n identity matrix. And if A is n by n, then this identity matrix, right, for matrix multiplication to make sense, that has to be an m by m matrix, because this m has to match up that m. And in either case, the outcome of this process is you get back the matrix A, which is m by n. So whenever we write the identity matrix I, very often the dimension, right, will be implicit from the context. So these two i's, they're actually different dimension matrices. One may be n by n, the other is n by m. But when we want to make the dimension of the matrix explicit, then sometimes we'll write it as I subscript n by n, kind of like we had up here. But very often the dimension will be implicit. Finally, I just want to point out that earlier I said that A times B is not, in general, equal to B times A, right? That, that for most matrices A and B, this is not true. But when B is the identity matrix, this does hold true. That A times the identity matrix does indeed equal to identity times A. It's just that, this is not true for other matrices B in general. So that's it for the properties of matrix multiplication and special matrices like the identity matrix I want to tell you about. In the next and final video on our linear algebra review, I'm going to quickly tell you about a a couple of special matrix operations, and after that, you need everything you need to know about linear algebra. In this video, I want to tell you about a couple of special matrix operations called the matrix inverse and the matrix transpose operation. Let's start by talking about matrix inverse. And as usual, we'll start by thinking about how it relates to real numbers. In the last video, I said that the number 1 plays the role of sort of the identity, right, in the space of real numbers because 1 times anything is equal to itself. It turns out that real numbers have this property that every number and that each number has an inverse. For example, given the number 3, there exists some number, which happens to be 3 inverse, so that that number times 3 gives you back the identity element 1. Right? And so, 3 inverse, of course, this is just 1/3, right? And given some other number, maybe 12, there's some number which is the inverse of 12, written as 12 to the minus 1, or really this is just 1/12. So that when you multiply these two things together, right, the product is equal to the identity element 1 again. Now, it turns out that in the space of real numbers, not everything has an inverse. For example, the number 0 does not have an inverse, right? Because sort of 0 inverse, so 1 over 0, that's undefined, right? Because 1 over 0 is not well defined. And what we want to do in the rest of the slide is figure out what does it mean to compute the inverse of a matrix. Here's the idea. If A is an m by m matrix, and if it has an inverse, I'll say a little bit more about that later, then the inverse is going to be written a to the minus 1, and a times its inverse, a to the minus 1, is going to equal to a inverse times a, is going to give us back the identity matrix. Okay? Only matrices that are m by m for some value of m have an inverse. So a matrix that is m by m, this is also called a square matrix. And it's called square because the number of rows is equal to the number of columns. Right? And it turns out only square matrices have inverses. So if A is a square matrix, so it's m by m, and if it is inverse, then it satisfies this equation over here. Let's look at a concrete example. So let's say I have a matrix 3, 4, 2, 16. So this is a 2 by 2 matrix. So it's a square matrix, and so this matrix could have an inverse. And it turns out that I happen to know the inverse of this matrix is 0.4 minus 0.1 minus 0.05, 0.075. And if I take this matrix and multiply these together, it turns out what I get is the 2 by 2 identity matrix, I. I can write this as I 2 by 2. Okay? And so on this slide, this matrix is the matrix A, and this matrix is the matrix A inverse. And it turns out that here I've computed A times A inverse. It turns out if you compute A inverse times A, you also get back the identity matrix. So how did I find this inverse? How did I come up with this inverse over here? It turns out that sometimes you can compute inverses by hand, but almost no one does that these days. And it turns out there's very good numerical software for taking a matrix and computing its inverse. So again, this is one of those things where there are lots of open source libraries that you can link to from any of the popular programming languages to compute inverses of matrices. Let me show you a quick example how I actually computed this inverse. And what I did was I used software called Octave. So let me bring that up. We'll see a lot more about Octave later. But let me just quickly show you an example. I'm going to set my matrix A to be equal to that matrix on the left. So I'm going to type 3, 4, 2, 16. So that's my matrix A, right? It's this matrix 3, 4, 2, 16 that I have down here on the left. And the software lets me compute the inverse of A very easily. When you type P inv of A equals this. And so this is, right, this matrix here, 0.4 minus 0.1, and so on. This is giving me a numerical solution to what is the inverse of A. So actually, let me just write inverse of A equals P inf of A. So set inverse of A equal to that. I can now just verify that A times A inverse the identities. And type A times inverse of A, and the result of that is this matrix. And this is 1, 1 on the diagonal, and essentially what, 10 to the minus 17, 10 to the minus 16. So up to numerical precision, up to a little bit of round-off error that my computer had in multiplying these two matrices. So up to low numerical round-off, these numbers off the diagonals are essentially 0. And so A times the inverse is essentially the identity matrix. And can also verify inverse of A times A is also equal to the identity with ones of the diagonals and values that are essentially 0 except for a little bit of round-off error on the off diagonals. In my definition of the inverse of a matrix, I had this caveat, right? First, A must always be a square matrix, but I had this caveat of if A has an inverse. Exactly what matrices have an inverse is beyond the scope of this linear algebra review, but one intuition you might take away is that just as the number 0 doesn't have an inverse, it turns out that if A is, say, the matrix of all zeros, then this matrix A also does not have an inverse because there's no matrix, or there's no A inverse matrix, so that this matrix times some other matrix will give you the identity matrix if this is a matrix of all zeros. And there are a few other matrices with properties similar to this that also don't have an inverse. But it turns out that in this review, I don't want to go too deeply into what it means for a matrix to have an inverse, but it turns out that for our machine learning applications, this shouldn't be an issue. Or more precisely, for the learning algorithms where this may be an issue, namely whether or not an inverse appears, I'll tell you when we get to those learning algorithms just what it means for an algorithm to have or not have an inverse and how to fix it in case we end up working with matrices that don't have inverses. But the intuition, if you want, is that you can think of matrices as not having an inverse if it's somehow too close to 0 in some sense. And to give just to wrap up the terminology, matrices that don't have an inverse are sometimes called a singular matrix or degenerate matrix. And so, this matrix over here is an example. The 0, 0, 0 matrix is an example of a matrix that's singular or a matrix that's degenerate. Finally, the last special matrix operation I want to tell you about is the matrix transpose. So suppose I have a matrix A. If I compute the transpose of A, that's what I get here on the right. This is A transpose, which is written A superscript T. And the way you compute the transpose of a matrix is as follows. To get a transpose, I'm going to first take the first row of A, 1, 2, 0. That becomes this first column of the transpose. And then I'm going to take the second row of A, 3, 5, 9, and that becomes the second column of the matrix A transpose. And another way of thinking about how to compute the transpose is as if you're taking this sort of 45-degree, axis and you're mirroring or you're flipping the matrix along that 45-degree axis. Okay? So here's the more formal definition of a matrix transpose. Let's say A is an M by N matrix, and let's let B equal A transpose. So let me say B equals A transpose like so. Then B is going to be an N by M matrix with the dimensions reversed. So here we had a 2 by 3 matrix, and so the transpose becomes a 3 by 2 matrix. And moreover, Bij is equal to Aj. So the Ij element of this matrix B is going to be the Ji element of that earlier matrix A. So for example, B12 is going to be equal to, look at this matrix B, B12 is going to be equal to this element 3, right? First row, second column. And that's equal to this, which is A21, second row, first column, right? And, which is equal to 2. And as another example, B32, right? That's B32 is this element 9. And that's equal to A23, which is this element up here, 9. And so that wraps up the definition of what it means to take the transpose of a matrix. And in fact, that concludes our linear algebra review. So by now, hopefully you know how to add and subtract matrices as well as multiply them, and you also know how what are the definitions of the inverses and transposes of a matrix. And these are the main operations you need in linear algebra for this course. In case this is the first time you're seeing this material, I know this was a lot of linear algebra material, all presented very quickly, and this is a lot to absorb. But but there's no need to memorize all the definitions we just went through. And if you download a copy of either these slides or of the lecture notes from the website, from the course website, and use either the slides or the lecture notes as a reference, then you can always refer back to the definitions to figure out, what are these multiplication, transpose, and so on definitions. And the lecture notes on the course website also has pointers to additional resources on linear algebra, which you can use to learn more about linear algebra by yourself. And next, with these new tools, we'll be able, in the next few videos, to develop more powerful forms of linear regression that can deal with a lot more data, a lot more features, and a lot more training examples. And later on, after linear regression, we'll actually continue using these linear algebra tools to derive more powerful learning algorithms as well.